Hi, this is Ms. Logan. Today I'll be talking about rotational motion. So this is part one. We'll be discussing kinematics, so motion in rotational motion. So the difference between rotational motion and circular motion. So right here is circular motion. In circular motion, something is revolving around something else. So there's a point and then something else is revolving around it. However, rotational motion is there's motion around a rigid body with an axis. So for instance, this is like a top or like the earth rotating on its axis. So there's not two bodies involved, there's only one, and it's rotating around itself. Now, rotational motion is different than linear motion. So when I say linear motion, I'm talking about what we did in Unit 1. So this is basic 1D and 2D motion. So if we look at this example, we have two lions that are revolving around this circle, okay? Now, when we're thinking about this, we may ask ourselves, how can we measure this in a more efficient way? So if our two lines move, we may have to figure out what is the distance that they traveled. If we would do typical linear motion, we would have to measure this line and we'd have to measure this line. This could kind of be confusing and also challenging because we're moving in a circle. So instead, we need to look at two different things. So we know this lion, let's say it's moving a radius of 1 around. The second lion is moving a radius of 3. So they have different radii, but they have the same angle. So remember, back to some geometry, that S, which is our arc length, is equal to R times theta. So it's important to remember that these lines that I drew are arc-like. Now, because it's not very far of a different distance, they kind of look flat, okay? So if we needed to figure out the distance they traveled, we would need to use this equation. So let's review some circle vocabulary. So first, a degree, one full turn around a circle is 360 degrees total. A revolution, one time around. We can also use rates per minute. So this would be the number of times we go around the circle in 1 minute. Last one is a radian. So once around a circle is 2 pi. Like I said before, or it's 360 degrees. We can also say that it's 1 revolution. All right, so just a reminder how to convert radians to degrees. So radians, I have pi over 180 times my degrees, so that these two cancel out and I have no units. Degrees is opposite, so I have 180 degrees over pi and radians, so these two will cancel out. So my question says convert 20 revolutions per minute to radians per second. So I have 20 revolutions per minute. Now, 1 revolution, we're going to radians, so that's 2 pi. And then 1 minute, I have 60 seconds. From there, I can multiply out and get my radians per second. Once again, here is the equation for figuring out my S, which is my arc length. This is something we'll be using throughout this unit. So when we go from translational motion, which we can also call linear motion, to angular motion, we actually are using the same exact formulas, except our variables are a little different. So in linear motion, we have delta x, and this is how far we traveled. Now we're going to have theta, which is in radians, okay? Instead of velocity, we have this omega symbol, which is radians per second, and acceleration, we have this alpha symbol, which is radians per second squared. So really we're just replacing our meters with radians. Here's another list of all of the different variables that we will change. We're going to be going over about to here today. And I'll give you a handout with some of these, but these are just how we're changing our equations and also our variables. Okay, so to look at how these equations are different, for velocity, we normally have s, so this would just be our distance over time. Now we have our delta theta over time. So this would be, remember, our radians over seconds. Acceleration, very similar, change in velocity over time. Now it's changed in angular velocity over time. Still, we're in radians squared over seconds. For displacement, from our old equation to our new equation, you'll see that the only thing that we're replacing are our variables for our distance and our variables for velocity and acceleration. And it's same with this equation here. So these are all of our equations for motion that we are translating from linear to angular. I'll take a moment right now to pause the video and look on your AP equation sheet for the different rotational motion equations. Now, how can we use this and how can we understand what we're doing? So a bicycle wheel has a radius of 1 meter and has a mass of 5 kilograms and is turning at 30 RPM. When the rider goes down a hill and applies the brakes, the wheel is going to turn 20 times until it stops. So we need to figure out the angular acceleration and how far the wheel is going to go. So first, we need to take this 30 RPM, which is our speed, and we need to put it in radians per second. So 30 revolutions per 1 minute. So in 1 revolution, we have 2 pi radians. These two cancel. And then in 1 minute, I have 60 seconds, and these two cancel. So that is going to give us 3.14 radians per second. So now let's solve for angular acceleration. So we are looking for the acceleration. So we know my initial velocity is 3.14 radians per second. Since we're applying the brakes, we know that my final is going to be 0. Now we need one more variable. Now remember that our distance is theta. So if we think about this situation, this wheel is going around 20 times, and each time it's going around 2 pi. So that's going to give us 40 pi all the way around. So if we go back to our equations, we're going to be able to use our omega f equals omega I plus 2 alpha theta. So once again, let's talk about what this means. So this is my final angular velocity equals my initial angular velocity plus 2 my acceleration and then my distance. Okay, so let's plug some things in here. So we're going to have 0 for our angular final, and then we're going to have our 3.14 for our initial, and then we have 2 looking for this, and then we have 40 pi. So our acceleration is negative because we're slowing down 0.039. And remember, this is radians per second squared. So the last part, it asks us for how far does it travel. So in this part, we need to use the S equals R theta. So we're looking for S, where we have S, and then R is our radius. And in this situation, our radius is 1. And then remember that theta is how far we travel. So in this one, it is 40 pi. So that's going to give us 40 pi, or approximately 125 meters. So when you're going through these problems, it's important to keep in mind your units. Make sure your units are canceling and everything is correctly in radians. All right, so our last topic is torque. So torque is what causes something to turn, or it's the product of the lever arm and the applied force. So if I have a door, and I have a doorknob right here. So I may push on this door from different angles. So I could push on it here, here, or here. And this is where my door hinges on the side. Now, if we think about this, and we'll do this in class, where is it easiest to turn? Well, that's in this area right here. Okay, I have a much larger product of my lever arm, and that's what I'm pushing on, and my applied force. It's much greater than in the center here, where my lever arm is shorter, my force is still the same. Our equation for torque is T is equal to RF, and if we have an angle involved, sine theta. Right now we're just going to worry about that RF part. Now the T for torque is a little t with a little wiggly hat on it. It looks a little bit different. So if we are setting up a problem, we need to think about how far away things are from each other. So if we look here, we have these two little guys, and they are sitting on a seesaw. And let's say that the seesaw is balanced. So we have two different sides. We have this side right here, and we have our other side. One way to describe this is clockwise and counterclockwise side, but I like to look at it with how they are even. So if we look on the left side first, we have this little guy. So his mass is M1, and he is R1 far away. On this other side, we also have something else, and that is the mass of the beam. So we have the mass of the beam, and that's R1 away. On the other side, we have the mass of 2, which is R2 away. And then we also have the mass of the beam, which is R2 away. From this point, we could actually solve for the mass of the beam. Okay, so with torque with angles, I'm going to have you watch a really great Khan Academy video after this that goes through it. But basically, our point of application and our lever arm must be at right angles. This will give us that the lever arm is R sine of the applied force and axis of rotation. Our last equation that we'll look at a little bit more, torque is also the resistance to change in rotational motion. So the other way that we can write this equation is torque equals I. I is our moment of inertia. We'll talk about that a little bit more in class and explore it more in depth, times our angular acceleration. So this moment of inertia, we are actually given this in most situations because it actually changes with the type of object. So right now, please watch and take notes for the Khan Academy video that I linked. In class, we're going to explore all of this and apply all of these different concepts.